So now let's proceed to the most advanced primitive that we discussed, most advanced in terms of reliability, which is uniform reliable broadcast. So let's see how we can implement URB. So before we can discuss the implementation of uniform reliable broadcast, we need to introduce the following important notion, which is called majority quorums. So majority quorums are very useful for implementing reliable distributed systems, as we will see. So let's define what they are. So below you have a mathematical definition, which is actually quite intuitive, as we will see. So first recall that this capital Pi is simply the set of all processes in the system, which we assumed to be known to everyone. And let's say that we have n processes in the system. So a majority quorum system is denoted by this letter, calligraphic Q. And this is a set which include all subsets of pi, which are as follows. So every subset in this in the quorum system, calligraphic Q, must include a majority of processes. Okay, so its size must be greater than n over 2. And also there must be at least one set in this collection Q, such that all processes in this set are correct. So this is the availability property. So one piece of terminology here, so all members of this system calligraphic Q, so all subsets that are included in this calligraphic Q are called quorums. Okay, so what these two properties mean? So first off, the consistency property implies that any two quorums intersect. Okay, so why it is the case? It is because every quorum has size which is which is greater than n over 2. It is a majority, and any two sets which include a majority of elements of some sets, or a majority of processes, they must intersect, right? So hopefully this is clear. Now, the implication of availability is that we must have at least a majority of processes which are all correct. Okay, so recall, there must be at least one set here such that all processes in this set are correct. And since all sets here, they include at least a majority, then that means that we must have at least a majority of processes which are correct. Okay, so this requirement, of course, restricts the failure resilience of the implementation of URB that we are going to consider, but it can actually be shown that in a fail-silent system it is necessary to have a majority of correct processes in the system in order to be able to implement uniform reliable broadcast. So here's the algorithm called Majority-Ack uniform reliable broadcast that implements the URB primitive. And this is the algorithm 3.5 in the textbook. So in this algorithm, just as we did in the RB algorithm, in the eager reliable broadcast algorithm, we have the internal instance of best effort broadcast that we are going to use for low-level message dissemination. So one interesting piece of state that we are going to keep in this algorithm is this array of arcs for every message M. Okay, so that is basically going to represent that a message is only gonna be ready for delivery once it gathered a quorum of acknowledgements. Okay, so we won't be delivering a message straight away after we received it from the best effort broadcast layer, as we did for eager reliable broadcast, but we're rather gonna wait until we have a majority of acknowledgements. Okay. So again, for the initial message propagation, we simply use the underlying BEB layer. Okay. So again, the most interesting part is this handler here, which is triggered whenever the BEB layer delivers us a new message. So when this happens, then first of all, we're gonna treat this message as an acknowledgement that the process that sent this message actually has this message. And for that reason, we are going to add the identity of this process, the identity of the sender of this message, to the set of processes that acknowledge it as having message M being received. Now, if this is the first time that we are seeing this message, okay, and that's indicated here by this line that message it does not belong to the set pending, then we do the following. So we are not going to deliver the message straight away, but rather we're gonna store this message in the pending set. Okay, so this is this line here. And then we're gonna trigger this rebroadcast of the message. So this is again the same idea as we have seen before. So we are basically echoing this message to all other processes. Okay, so just to recap, when we get the message for the first time, we are not delivering it straight away, because we first want to verify that is actually being available at the majority of processes. So we store the message and then we echo this message. Okay, so notice that we discussed that this broadcast of a message is delivery of a broadcast of a message is also interpreted as an acknowledgement of a process having this message. So this rebroadcast here, it's not only its objective not only propagate this message, but also let everyone know that this message is actually available at that process. Okay, so this is the echoing step here. Right, so this is very important. So this is actually one of the main points about this algorithm, that that the order of delivering and echoing is switched compared to the eager reliable broadcast algorithm. Okay, so we first echo and then at the later point we will deliver. Okay. All right. And when the message can be delivered, so this can happen when it is actually acknowledged by a majority of processes. And this is captured by this can deliver function, which basically, so this pound sign, this hash sign here, means that basically just to take the number of elements in this set. Okay, so if the number of elements in this set, if the number of arcs is greater than a majority, then this function is going to return true. Okay, and then this function, this predicate is being checked here. So we have like a guarded event handler here. Okay, so can deliver is actually checked here. So if can deliver is true, and we have this message available, so we already heard it, we stored it in the pending set, then we can actually deliver this message. Okay. So this is the algorithm, and this is actually important to see why it is correct. And so this idea with waiting for a majority of facts becomes clear. Okay, so let's see how the proof goes. So first off, the first three properties are easy. So to prove URB1 to URB3, we can simply reuse the respective proofs of RB1 to RB3 for eager, reliable broadcast. So the most interesting part is, of course, to show that uniform agreement holds. So to prove uniform agreement, let's just consider an arbitrary message M, which is URB delivered by some process P. So notice that we are not asking this process P to be correct. It can be any process. Okay, so if that happens, then we also have that M was acknowledged by a quorum of processes. Okay, so there is some set Q, which is of size greater than half, so Q is a quorum. Okay, so it includes a majority of processes, and all processes in Q acknowledged to have M received from the best effort broadcast layer. Okay, so this is the first step, and this actually follows from this function can deliver, which is used as a guard for URB delivering a message, right? So we want URB deliver a message unless can deliver is true, and can deliver can only be true if the message was acknowledged by a majority, by a quorum. Okay. So now, since any two quorums intersect, and as we said, we have this availability property by which there is a quorum in which all processes are correct, we must have at least one process in this set Q that acknowledged M, which is correct. So since Q is correct, it must have equated M by means of the BEB broadcast. Okay. And so by the validity property of best effort broadcast, this implies that all correct processes will BEB deliver message M, which means that they will also echo M. Okay. And finally, since we have at least a majority of correct processes, and all correct processes, as we said here, are guaranteed to echo M through best effort broadcast that is available to them, then simply by the properties of BEB, again, by the validity of BEB, all correct processes will eventually receive all these echoes, and they will treat them, as we discussed, or every message is received also treated as an ACK. Okay, so they will treat it as an ACK, and they will eventually have a majority of ACKs for message M, which implies that they will be able to URB deliver M. Okay, so we get that, so we started from message M, URB delivered by some correct process, and we went through these steps and we ended up here with the statement that M is delivered by all correct processes. And this is exactly what uniform agreement implies. Okay, so that completes the proof. And here we use the properties of quorums that at least one correct process must have acknowledged the message, receiving the message. And this process would have propagated, or actually propagated the message to all other processes, all other correct processes, which also acknowledge that message, and that eventually produces enough acknowledgements in the system to allow M to be delivered by everyone.